Hi kids, our notes now are over 1.4 beginning proofs and 1.5 division of segments and angles. Our essential question is how can I write simple two-column proofs and how can I prove midpoints, trisection points, and bisectors or trisectors of segments and angles. Here are our first two theorems that we will use in a few moments in some two-column proofs. The first one says, if two angles are right angles, then they are congruent. We know that right angles are angles that equal 90 degrees. So if two angles both have the same measure, then they are congruent. We also know this second theorem, which says, if two angles are straight angles, then they are congruent. We know that straight angles by definition equal 180 degrees. So if two angles both equal 180 degrees, then they are congruent. So here's our first example of writing a proof. In this proof, we have a picture of what looks like a rectangle, ABCD. We also have some givens, and the conclusion is what we're trying to prove. The givens are that angle A is a right angle and angle C is a right angle. We're trying to prove that angle A is congruent to angle C. The very first thing I always tell my students to do is to put the givens on the picture. So if A is a right angle, we will show that with our little square in the corner and also with angle C because that's our other given. So the way that we do these proofs is there are two columns. The left column, these are called your statements. In the right column, these are called your reasons. The purpose of a two-column proof is just a nice way to organize yourselves and think through a problem. If you recall when we solved those equations or we reviewed them, we wrote out to the side the reason we were able to go from one step to the next. It's very similar to what we have here. So the way this works, the statements are what we know and the reasons are how we know them. So the first things that we know is that angle A and angle C are right angles. So we're going to state that. Angle A is a right angle, and please feel free to abbreviate here to kind of save you a little time. And angle C is a right angle. Now under the reasons column, the reasons why we know this is because they were both given to us. So I always put down my givens first. Then we look at that conclusion. It says angle A is congruent to angle C. Well, we just learned a theorem that says if two angles are right angles, which is what we have, then they are congruent. So by that theorem, we are able to state our conclusion, which is that angle A is congruent to angle C. And the reason we put is that first theorem we learned. We're going to actually write it out, but like I said, please feel free to abbreviate. If two angles are right angles, then they are congruent. You can just say then congruent. And there is a two-column proof. Let's try another example. In this one, our given says diagram. That means the only thing we know is based off of our picture. We are trying to prove, which is the same as the conclusion, that angle EFG, that's this guy, is congruent to angle HFJ, that's this guy. Okay, so if we look at our picture, what do we know from our picture? We know that those two angles are straight angles. We also have just learned theorem 2, which says if two angles are straight angles, then they are congruent. So I think that's how we're going to use what we know from the picture to get to our proof statement. So let's go ahead and set it up. Statements on the left, reasons on the right. The first thing we're going to put in our proof are our givens. Our givens are from our diagram. So the thing from our diagram that we need is that we've got those two straight angles. Remember, assuming angles are straight is something that is safe to assume. The first angle that is straight is angle EFG. So angle EFG is a straight angle, and angle HFJ is a straight angle. Now the reason can't be given because it's not listed as a given. We got these givens from our picture. So what we're going to do is write assumed from diagram. And I'm just going to abbreviate here. Because we need to write this on both lines, rather than rewriting it, I can just use these double quotations, and that means repeat from the previous line. So that's another way to save time and effort. You'll love these proofs. Okay, so what do we know? Look at our statements. We have this angle straight, this angle straight. Because of that, we can say, based on Theorem 2, that if two angles are straight angles, then they are congruent. So we can say that angle EFG is congruent to angle HFJ because of that theorem. That's what we're going to write for our reasons. Please, again, feel free to abbreviate. If two angles are straight angles, I don't even mind if you abbreviate straight, then congruent. And there's another proof using one of our new theorems. All right, let's take a look at our last example from section 1.4, these beginning proofs. We have some angles in a picture. We know that the measure of angle RST equals 50 degrees. I'm going to add that to my picture. We know that the measure of angle TSV equals 40 degrees. I'm going to add that to my picture. And we know that angle X is a right angle, so I'm going to add that to my picture with a little square box. We're trying to prove that angle RSV, which is this larger angle, these two together, is congruent to angle X, which is the right angle in the corner. So let's go ahead and set up our proof. We've already labeled our givens on our picture. Statements and reasons. Okay. One of our theorems states, we only know two of them, is that if two angles are right angles, then they're congruent. We already know that angle X is a right angle. If we could prove that angle RSV is a right angle, then we know that they are congruent. Now if we look at RSV, it's made up of RST and TSV, which are 50 and 40. And if we add those together, we get 90. And by definition of a right angle, a 90-degree angle is a right angle. So we can go about it that route. So I'm going to first start with my two givens. Now generally I like to put all my givens at the beginning under my statements, but you can also list givens as you go and as you use them or need them. You will usually use all of your givens though. So I'm going to start off with the first two. The measure of angle RST equals 50 degrees, and the measure of angle TSV equals 40 degrees. And my reasons, of course, for both of these are givens. If it helps you to kind of stay in line, you could check off the givens as you use them so you know which ones you have left. So we need to prove that RSV is a right angle. Well, if these two add up to 90, then that will be the way. So I first need to state that the measure of angle RSV equals 90 degrees. And I know that by addition, because I know that 50 plus 40 is 90. Easy peasy. Now I can say that angle RSV is a right angle. And I know that because that is the definition of a right angle. The shorthand for definition is DEFN with the line above the N. I don't know if you can text that, but that's the shorthand you can use a lot in this class. So we can just say definition of right angle. Now that I know that I have a right angle there, I can state that angle X is a right angle. Run out of room here. That is one of our givens, so our reason will be given. I'm going to check that off. I've used all my givens now. The last thing is our statement. the last thing is our proof statement. And forgive me for erasing that, but I was running out of room. So feel free to rewind if you need to. But now we can state our proof statement, which is that angle RSV is congruent to angle X. The reason being because of that first theorem that we learned. If two angles are right angles, then they are congruent. And there you have it. Okay, now we're starting the 1.5 part of the notes, which is about bisectors and trisectors of segments and angles. So the first thing we're going to talk about is a segment bisector. Bi means two. Anytime we take a segment and cut it in half, we are bisecting it. That means to divide into two congruent equal parts. And we divide it at the segment's midpoint. That is the point where we cut it in half. So if I have, for example, this segment AC, and let's say I want to bisect it with a line. Note I can bisect a segment with a point, segment, ray, or line. Let's say somehow I figure out where the middle of that is. There's my line. That point right here that cuts AC right down the middle, that is the midpoint. Let's call it B. That is the midpoint. That is the halfway point between A and C. Midpoint of segment AC. Because that is the midpoint, I know that segment AB and segment BC are congruent, and I can show that with tick marks. So there's a couple of things we can say here. We can say that segment AB is congruent to segment BC. We can also say that the distance between A and B is equal to the distance between B and C. If you know that A, B, and BC are equal, the reverse is also true, then I know that B is my midpoint. So on some of the proofs in this section, you will be trying to prove midpoints, and you can do that by showing that this part and this part are congruent. If you can make that statement, then you could say that B is the midpoint by definition of midpoint. This line right here, this is the segment bisector. Remember, a segment bisector is anything that cuts another segment in half. It can be a ray, a line, a point, or a segment. Just like we can bisect a segment, we can also trisect a segment. Where we needed one bisector to bisect a segment, we need two trisectors to trisect a segment into three congruent parts. Again, they can be points, segments, rays, or lines. And the points at which the trisectors intersect with the segment, those are called the trisection points. So for example, if I have segment EH and I decide to intersect it with this line here and this line here, and it just so happens that this point of intersection F and this point of intersection G ends up creating three congruent segments, EF, FG, and GH, then I can say that points F and G are trisection points. The two lines were the segment trisectors. That's this line and this line. And the way we can write this in symbols is segment EF is congruent to segment FG, which is congruent to segment GH. Or we can say the distance between E and F is equal to the distance between F and G, which is equal to the distance between G and H. If we are trying to prove that we have trisection points, we need to first prove that we have 3 congruent segments. Just as segments can be bisected and trisected, so can angles. We've got 2 angles here. One we're going to bisect, one we're going to trisect. The angle on the left, angle ABC, if I was to draw something from vertex B, let's put a point here called D, which created 2 congruent angles, then I know that this ray BD is my bisector, my angle bisector, called the angle bisector. Okay, I also know that I can write angle ABD is congruent to angle DBC, or I can write the measure of angle ABD is equal to the measure of angle DBC. Okay, so very similar to the segment. We can also trisect an angle. So if we look at the angle on the right, angle RST, I'm going to need 2 things to trisect something. So let's say I have let's have these be segments this time. And we'll put U and V here. If I draw these 2 segments also intersecting at vertex S, and it just so happens that this angle is congruent to that angle, which is congruent to that angle, then I can say that this segment US and the segment VS, I can say that those are angle trisectors because they have split this angle into 3 congruent angles. We can also say that angle RSU is congruent to angle USV, which is congruent to angle VST. And then I could also make a similar statement to this one right here, saying that their measures are also equal. Okay, here's one last example. We've got a given, we've got a picture, and we've got a question. Rather than a proof or conclusion, we actually just need to answer this question. So sometimes you're not going to be always doing 2-column proofs. Sometimes you'll physically be finding a value or answering a question. So in this case, it tells us that OM equals. Notice that this equals sign right here indicates a number. So all of these are indicating values, which means, hey, we might be able to set up some equations here. I always like to, like I said, put my givens on my picture. So the distance between O and M has a length of x plus 8. The distance between M and P has a length of 2x minus 6. And the distance between O and P is 44. Okay, this is kind of like the problem we did in class the other day. I can see from this picture that if I add OM to MP, it should equal 44. I don't know at this moment if M actually is the midpoint. If it is the midpoint, then I could say x plus 8 equals 2x minus 6. But at this point, I do not know that. So I'm going to have to first figure out what x is by setting up this other equation. This is what we said. We said x plus 8 plus 2x minus 6 equals 44. That we can be sure of. So let's go ahead and solve this and see what we get. If we combine like terms, we get 3x plus 2 equals 44. If we subtract 2 from both sides to get our constants on the right, then 3x equals 42. And then if we divide both sides by 3, we end up getting x equals 14. Okay, so this x equals 14 is really important to us. Now we can go back into OM and NP and evaluate them. If M truly is in the middle, then each of those will be equal. So let's evaluate OM. OM is x plus 8. In this case, x is 14, and 14 plus 8 equals 22. Some of you are thinking, oh, that's all we need to know, because they know that half of 44 is 22. But just to prove that MP has the same length, we're again going to plug in 14 into its expression, which is 2x minus 6. 2 times 14 minus 6. 2 times 14 is 28, minus 6 is 22. So if MP also equals 22, I can now say that those two segments are congruent. And if those two segments are congruent, then M is my midpoint. So the answer to this would be yes. That's it. See you in class.